Okay, good morning. This is Professor David J. De Los Reyes. Okay, my topic for this session will be AC machines. Okay, and I am now on lesson number 30. We are now on lesson number 30. Okay, let's proceed. The subject matter for this morning will be AC machines, lesson number 30, example. The title of the topic will be example problem on the parallel operation of transformers. Okay, I will bring out an example problem on the so-called parallel operation of transformers. This is actually a continuation of the last topic because the given from this problem is actually emanates from the last example under lesson number 29. Okay, let's proceed. If the tap of transformer number 2 is shifted so that the voltage rating is the same as that of transformer number 1, referring to the last problem under lesson number 29, okay, which is 4600 over 230, meaning if we change the voltage specification of transformer number 2, meaning to say the tap of transformer number 2 is adjustable, it's just like a barrier, so we could actually change the voltage specification to become 4600 over 230. Okay? Calculate the load assumed by each of the transformers for a total load of 20 kVA. Okay, let's try to bring out or analyze the problem. What is given is actually transformer number 1. The voltage specification is 230. No, 4600 over 230, meaning the primary is 4600, secondary is 230. The equivalent impedance referred to the primary is 0.16 and the rating is 10 kVA. For transformer number 2, the original voltage specification is actually 4485 230, meaning the primary is 4485. It's different from this. Okay? But according to this problem now, if we change the tapping of transformer number 2 so that the voltage specs will now become 4600 K primary, same as the first one, and the secondary will be same as the first one, and the equivalent impedance referred to or for transformer number 2 is 0.22, the rating is 7.5 kVA. The problem is asking for a total load of 20 kVA. What will be the current, what will be the apparent power carried by transformer number 1 and what will be the apparent power carried by transformer number 2 for a total load of 20 kVA. The total load is 20 kVA. With the given specification, voltages are the same, 4600 to 230, but their impedances are actually different. First one is 0.16, second one is 0.22. Okay? Okay, let's try to bring out the figure for this one. The figure for this one, this is BP over A. This is now the simplified circuit diagram. And we are having two transformers, okay, delivering a load to a total load of 20 kVA. Right? This is CS 1.16, this is CS 2.22. Subscript number 2 refers to transformer number 2 and subscript number 1 refers to transformer number 1. So the current delivered by transformer number 1 is IS1 and the current delivered by transformer number 2 is IS2. And the total current passing through the load should be I sub L. Okay, so the problem is asking for a total load of 20 kVA, how much will be the load carried by transformer number 1 and what will be the load carried by transformer number 2. Out of the 20 kVA, how much is for transformer number 1 and how much is for transformer number 2. Okay? Okay, let's try to bring out the solution of this one. Using the current divider principle. Current divider meaning for a parallel circuit, okay, the voltage across this is equal to the voltage across this. Okay, we equate it. There is an equality. That is the so-called current divider principle, right? The voltage across this is actually I is 1 times CE is 1. And the voltage across this will be the current passing through it times its impedance. That is IS2 times CS2. Solving for IS1, okay, IS1 will be CES2 over CS1 times IS2. It's just algebraic manipulation. We multiply this by 1 over CES1. So the left hand side multiplied by 1 over this will disappear. The left hand side will just be simply IS1. For the right hand side, it will be IS2 CES2 times 1 over CES1. So it will be CES2. The ratio of CES2 over CES1. It is this. Right? And we are now given the values of the impedances, right? It's 0.22 over 0.16 times IS2. So we produce a linear equation involving the two currents, okay? And we call it equation number 1, that is IS1, the ratio of 0.22 over 0.16 is 1.375 times IS2. We call this equation number 1. We produce the linear equation involving IS1 and IS2, and the relation is IS1 equal to 1.375 times IS2. Meaning, the current carried by transformer number 1 is bigger. It is 1.375 more than IS2. So, actually, IS2 is smaller. Right? That will be equation number 1. From the figure, am I still in camera? From the figure, the sum of IS1 plus IS2 is equal to IL. So IS1 plus IS2 equal to IL. Okay? And we could compute for the value of I sub L. We are given the total load, right? The total load is 20 kVA. We convert that to volt ampere. We multiply that by 1000. Okay? And we divide that by 230. Okay, what comes out is 87 amperes. Meaning to say, for a total load of 20 kVA at a voltage of 230, the total current is 87 amperes. So if we try to go back here, IS1 plus IS2 should be equal to 87, and that will be equation number 2. So again, we produce a linear equation involving two unknowns, that is IS1 plus IS2. So this is a problem of algebra. Okay? If we try to take the value of IS1 to be equal to this, we put it on equation number 2. Okay? So IS1 from equation number 1 is 1.375 IS2 plus IS2 equal to 87. Similar terms, right? 1.375 plus 1 will be 2.375. Then we'll try to multiply all the terms by the sum of this is 2.375, so this is 1 over 2.375, right? If we try to take this up, similar terms. So for the left hand side, this one cancels. The coefficient of the left hand side will be 2.375, right? So it will cancel with this. What remains will be IS2, and this should now be equal to, the right hand side will be 87 times 1 over this, that is 87 divided by 2.375. The coefficient of the sum of this is 2.375, and what comes out for IS2 is 36.6 amperes. Right? So we could go back to equation number 1, and we could compute for IS1, and IS1 will be 1.375 times 36.6, and this is 50.4 amperes. So for us to determine the apparent power carried by each transformer, we will use the equation volt ampere equal to EI, right? Right? So if this is kVA, we will divide this by 1000. Right? So for kVA, the apparent power carried by transformer number 1, it will be H voltage, 230. Their secondary voltages are the same to be 230. The total current carried by transformer number 1 is actually 50.4. So this is 50.4. Okay, sorry for this one. This is over 1000. For it to be kVA. Over 1000 and it will be 11.6 kVA. For transformer number 2, the voltage is still 230. Similar voltage, right? Secondary. So this is 230. The current carried by transformer number 2 is actually 36.6. So this is 36.6 over 1000 to convert it to kVA. And what comes out will be 8.4 kVA. And if you try to take the sum of these, 11.6 plus 8.4 is actually 20 kVA. Right? The total load is 20 kVA. So with the specification, this is 0.16 and this is 0.22 as impedances. Okay? What comes out for the proportionality of the load that is carried by its transformer is that kVA number 1 is 11.6 and kVA number 2 is 8.4. They are a little bit overloaded because the rating of transformer number 1 is still kVA. This is 11.6, this is 7.5, and this is 8.4. The overload is not so much, so it's just fine. But the main concern of the problem is how much is the load carried by each of the transformers. Okay, number 1, it is 11.6. Number 2, it is 11.4. Okay? Okay, good morning from Los Angeles. This is Professor David J. Del Suel.